All right, so here we are picking up with yet another type of quantitative data display, and it is built around this idea of a 5-number summary. The 5-number summary is a report that's going to give you the median, or if you were to arrange the values from smallest to largest, the value with 50% equal to or less than the value, the quartiles, which is where 25% or 75% of the data is equal to or less than, and the extremes, which are going to be your maximum and your minimum. Now, a lot of times you're only going to be given these 5 numbers, and you need to be able to recognize before you begin any problems what exactly is going on. Is this data going to be skewed? Is it going to be symmetric? We're not going to be able to tell about modes with this, but we can gather a lot of information. So one of the visual ways that we do this is through the box plot. Now, this isn't the really basic box plot. We actually have what's called the box and whisker plot, and it's going to be extremely helpful for us when we want to compare groups because it's a nice and simple way to check side by side what's going on. They're also really helpful because you can tell at a glance whether or not you have outliers in your data, and outliers themselves play a huge role in our data summaries and whether or not we're able to take our data and use that to then infer towards a larger set of interesting populations. So here you can see a good comparison of box plots versus histograms, where in this first display we have our uniform distribution, and a uniform distribution is going to show in a box and whisker plot because each of these segments, the first quartile, second, third, and fourth, are all going to be of the same general length. Whereas when we have symmetric data, we can see here that my interquartile range, that's the distance between quartile 3 and the marking for quartile 4 and the marking for quartile 2, that's going to be smaller than my 2 whiskers. And these lovelies, these circular points, show me that I actually do have outliers in my data, both a high and a low end outlier. And we're going to work in a little bit as to how to calculate what an outlier actually is. Now, for the skewed data, it really does lean well to that idea of this is the tail. Skewed left has the tail on the left, and you can see here it looks much more like a longer tail heading towards the lower values. Remember, skewed left doesn't always have to be left to right. It can be vertical, and it can be inverted in the order of your numbers. Skewed left is always where the tail is with the lower values. So one of the big things you want to be careful with is don't worry if a box plot is drawn vertically. That's used a lot of times simply because, well, it takes up less space. Just keep in mind, again, skewed left means the tail is towards the lower values, whereas skewed right, the tail is on the higher values. So again, try to clear your mind from that left and right and think lower and higher. So the interquartile range is a very important piece of data that we use to describe quantitative data. To find the interquartile range, you arrange all your values from smallest to largest, and you take your third quartile value and your first quartile value. The third quartile value is where you have 70% of the values at or below a certain point. So let's say I had 10 numbers. I would say 10 times 0.75, and that's going to be 7.5. So I'm going to look at what would be between the 7th and the 8th position, and you would take what was in the 7th position at or below. This isn't going to be one of those where you average the two values. This says, again, 75% of the data is at or below that given value. And the 25th percentile works the same way. Once you find your interquartile range, that is then used as a tool to determine your fences, where each fence is going to take one quartile and going to add or subtract 1.5 interquartile ranges from it. So for your lower fence, you take the smaller quartile, quartile 1, and you go minus 1.5 interquartile ranges, so you're moving away from center. And the upper fence does the same thing. You're going to be moving away from center at that third quartile. So you're going to have quartile 3 plus 1.5 interquartile range. Now, these fences dictate for us where our outliers begin. If something were to happen to land perfectly on a fence, so exactly 1.5 interquartile ranges away from those markings, then it's just a regular data point. As soon as you are beyond that fence, even the tiniest bit, we consider it an outlier. And we extend this definition and say that if a value is more than 3 interquartile ranges away from Q1 or Q3, then we call those extreme outliers. And that's not saying we're going to fill something else in. That little asterisk, that star, is how we indicate it on a box plot. A regular outlier is just going to be a circle. Sometimes you'll see them displayed as squares just for computer sakes, but an extreme outlier is always going to be denoted by an asterisk. Now, this is the main reason why I wanted you guys to be able to view this video before coming to class. I really want you to make sure that you take these notes and you understand how to construct a box plot from start to finish. So when we draw a box plot, you need to decide whether you want it vertical or horizontal. It really doesn't matter. Typically, I think about which one's going to be a better use of space, and if I'm comparing multiple groups. Just kind of go with that. So I'm going to draw here a single vertical axis, and you want to make sure that that axis is going to span the entire range of data. That means on your axis, the numbers that you have represented, again, this is just like a histogram, these are going to start me and set up my scale. It's going to fully cover the range of all data from the minimum to the maximum. Then what you're going to do is you're going to draw short horizontal lines at quartile 1, the median, and quartile 3, and you're going to use that to create a box, hence box and whisker. So now comes time for the whiskers. So in order for us to build our whiskers, again, you find your fences. So what you're going to do is you will make your 1.5 interquartile ranges above, 1.5 interquartile ranges below, and these are going to be your fences. Now, with the fences, these are not actually going to be physical parts of my graph, but they are going to be kind of guidelines for us. So you see here, I've got that drawn with a dashed line because we may or may not be actually drawing in where that fence is. Once you have that, you're going to draw your whiskers. So you've established where your fences are, and you are going to extend a line from the box up to the last data point that is either equal to or within the fences. Okay, so again, doesn't necessarily have to go all the way to the fence. You go to the last data point within the fence. If a data point is outside the fences, you're just going to be drawing dots. You're not going to be drawing the whiskers. So you can see here, my data did not fully hit the 9, so I don't actually go to the fences. So we have, with this graph here, a typical outlier display. On the TIs, they use a lot of times a square box simply because of pixelation. It's easier for them. It really does not matter for me, but please understand that if you have extreme outliers, you do want to make sure that you use your asterisks. So this here is my interquartile range. This here is 1.5 interquartile ranges from it. If I were to extend that distance again, that would give me 3. And it's questionable because I don't have the exact numbers whether or not this here is extreme outlier, but if it was an extreme outlier, you would simply draw it with an asterisk. Okay, so hopefully you guys had an opportunity to write all of that down. It's very important you understand how to do this. We're going to be working in class how to use your calculator to do this for you, but even with that, you need to understand the construction methods, because justifying why something is an outlier or why it isn't, and using these ideas of interquartile ranges are going to become extremely important for us. And just looking at your calculator is not going to be enough.